The San Andreas Fault did not suddenly split open. It did not produce a magnitude 8 earthquake, and there is no official countdown to California's next disaster. What happened is quieter, more technical, and in some ways more unsettling. A new physics-based reconstruction of 1,000 years of earthquake history found that key parts of the southern San Andreas and neighboring San Jacinto fault systems have entered a modeled stress configuration that researchers had not expected to see so clearly. One segment reached 3.6 megapascals of accumulated Coulomb stress in the model, higher than any comparable value in the reconstructed millennium. Another major segment of the San Andreas reached 2.8 megapascals. More important, the two sides of a critical junction northeast of Los Angeles are becoming highly stressed at the same time. That junction is Cajon Pass, and scientists now describe it as an earthquake gate. Sometimes it stops a rupture. Sometimes it allows a rupture to cross from one major fault system into another. Today, we are going to break down exactly what the new study found, what the San Andreas actually did, where the danger is greatest, and whether the situation could become worse. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally felt an earthquake in California or anywhere else? Tell me where you were and what the shaking felt like. If you want to be the first to know every time something major happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one so the algorithm actually shows it to people who need to see it. Now, let us get into it. The story begins not with a sudden tremor, but with a paper published in June of 2026 in the Journal of Geophysical Research, Solid Earth. The research team included scientists from the University of Bern, the University of Hawaii at Manoa, the United States Geological Survey, and the Scripps Institution of Oceanography. Their target was one of the most complicated pieces of earthquake terrain in North America, the place where the southern San Andreas Fault approaches the San Jacinto Fault near Cajon Pass, roughly northeast of the Los Angeles basin. On a road map, Cajon Pass looks like a transportation corridor cut through steep mountains. Interstate 15 runs through it. Freight trains climb through it. Power, fuel, communication, and water systems cross or approach the same narrow region. On a tectonic map, however, the pass is a junction between fault segments that can behave separately or, under the right conditions, participate in one much larger rupture. That distinction is the center of the new finding. Researchers did not place a pressure gauge directly inside the fault and read a number from a dial. Stress several miles underground cannot be measured that way. Instead, the team built a 4-dimensional earthquake cycle model. 3 dimensions represented the geometry of the crust and faults. The 4th dimension was time. They reconstructed approximately 1,000 years of large earthquake history using paleoseismic evidence, including disturbed sediment layers, radiocarbon ages, tree ring anomalies, mapped surface ruptures, and historical accounts. Then they simulated how each earthquake would release stress on the part of the fault that broke, transfer stress to nearby segments, and leave the deeper crust and upper mantle to relax gradually over decades and centuries. The model ran from the year 1100 through 2025. It treated the crust as an elastic plate over a deeper layer that can deform slowly, somewhat like a very stiff material that bends back over long periods after being disturbed. Plate motion kept loading the faults during the quiet years. Every simulated rupture reset stress on the broken segment, while nearby sections could remain loaded or even receive additional stress. The result was not a schedule of future earthquakes. It was a moving map of how the mechanical state of the fault system may have evolved. That moving map produced the number that drew attention. By 2025, modeled Coulomb stress reached about 2.8 megapascals on the Mojave South segment of the San Andreas Fault. It reached about 1.8 megapascals on the North San Bernardino segment. On the San Jacinto Bernardino segment, the modeled value reached 3.6 megapascals. In the researchers' 1,000-year reconstruction, that 3.6 value exceeded the highest pre-event level seen anywhere in the modeled record. To put 1 megapascal in context, it equals 1 million pascals of pressure, or roughly 10 times standard atmospheric pressure. But that comparison can be misleading if taken too literally. A fault does not fail because a simple pressure tank reaches one universal number. Rock strength, friction, pore fluid pressure, fault orientation, temperature, roughness, and past damage all matter. Coulomb stress is best understood as a calculation of whether the combination of shear stress trying to make the fault slide and normal stress clamping it shut has moved the fault closer to or farther from failure. The model estimated characteristic pre-earthquake ranges for the 3 nearby segments. Mojave South showed past failure behavior in a modeled range of about 1.2 to 2.7 megapascals. North San Bernardino showed about 0.4 to 1.6. San Jacinto Bernardino showed about 1.2 to 2.9. The present modeled values were at or above the upper parts of those ranges. That does not mean the faults must rupture immediately. It means the model places them in a mechanical state comparable to, or more loaded than, states preceding major ruptures in the reconstructed past. But here is the part nobody expected to become so important. The absolute stress on a single segment may not be the deciding factor at Cajon Pass. The difference between the stress levels on neighboring fault systems may help determine whether the gate stays closed or opens. The historical comparison is stark. On December 8, 1812, a large earthquake struck near Wrightwood. The exact rupture extent remains a subject of scientific reconstruction, but geological evidence indicates that the event involved the Cajon Pass region and is associated with rupture behavior that crossed or linked the San Andreas and San Jacinto systems. In the new model, stress on the neighboring segments was high and relatively aligned. The gate was open. 45 years later, on January 9, 1857, the magnitude 7.9 Fort Tejon earthquake tore along roughly 225 miles of the San Andreas Fault. In places on the Carrizo Plain, the ground shifted horizontally by as much as about 30 feet. The shaking lasted roughly 1 to 3 minutes across parts of central and southern California. Yet the rupture stopped near Wrightwood, north of Cajon Pass, and did not continue down the San Jacinto system. In the model, stress conditions around the junction were less evenly matched. The gate was closed. This is why the new work changes the picture. Cajon Pass is not simply a permanent wall in the fault system. It is not a fixed doorway that always opens. It behaves more like a mechanical switch, whose state depends on the loading pattern built by centuries of plate motion and previous earthquakes. When the neighboring segments are stressed together, a rupture may have a better chance of continuing through the junction. When one side is much more loaded than the other, the rupture may lose the conditions it needs to keep moving. The current modeled configuration is uncomfortable because Mojave South and San Jacinto Bernardino are both highly loaded. Their values are not identical, but they are closer to the kind of joint high-stress condition the team associated with through-going ruptures. In other words, the unexpected development is not that the fault visibly jumped today. It is that the reconstructed system appears to have quietly moved into a state where the gate may be more permissive than scientists would want. That changed fast in the public conversation. Headlines described the highest stress in 1,000 years. Some posts treated the study as proof that the big one was imminent. Others claimed that a quake could be predicted within weeks. Neither statement is supported by the research. The lead author emphasized that the study does not predict when an earthquake will occur. The United States Geological Survey states plainly that no scientist can currently predict the exact time, place, and magnitude of a major earthquake. A model can identify concerning conditions. It cannot provide a countdown clock. There is also a crucial distinction between modeled stress and direct observation. The research combines real fault geometry, geodetic slip rates, and a long record of past ruptures. But every model simplifies reality. The earthquake record before modern instruments is incomplete. Dates and rupture lengths reconstructed from trenches carry uncertainty. Slip rates are not perfectly uniform. Some parts of the San Andreas creep continuously, while others remain locked. The model also assumes that a rupture fully resets resolved shear stress on the segment that breaks. Nature may leave more complicated patches of residual stress. Earthscope's review of the work pointed to these limitations directly. The Paleoseismic record is extensive but not perfect. The San Andreas and San Jacinto do not produce small earthquakes at identical rates, and scientists do not yet fully understand why. Fault friction varies. Fluids move. Small branches can redistribute stress. The crust is not a clean set of flat surfaces. It is fractured, folded, and damaged. None of those limitations makes the result meaningless. They define what the result actually is, a physics-based estimate constrained by the best available evidence, showing that current conditions deserve attention. Science becomes more reliable when uncertainty is stated, not hidden. To understand why the stress continues building, we need to step back and look at the San Andreas itself. The fault system extends more than 800 miles through California and reaches at least about 10 miles into the crust. It marks the broad boundary between the Pacific Plate to the west and the North American Plate to the east. The Pacific Plate moves northwest relative to North America at roughly 46 millimeters, or about 2 inches, per year. 2 inches sounds harmless. It is about the rate at which fingernails grow. But multiply that movement by decades, lock parts of the boundary with friction, and spread the stress through hundreds of miles of rock. The plates keep moving even when the fault surface does not. Elastic strain accumulates in the surrounding crust. Roads, survey markers, and satellite-measured points on opposite sides of the system slowly distort relative to one another. When friction can no longer hold a locked patch, the stored strain is released in seconds. Not every section behaves the same way. Parts of the central San Andreas creep, sliding gradually and producing many small earthquakes. Other sections are locked. The southern San Andreas, including areas near the Salton Sea, Coachella Valley, San Gorgonio Pass, and Mojave segment, contains long locked stretches capable of producing major earthquakes. The San Jacinto Fault runs nearby and accommodates a substantial share of the regional plate motion. Together, they form a network, not a single clean crack. Think of the system as a set of heavy railroad cars connected through switches. Plate motion is the locomotive pushing continuously from behind. A locked fault segment is a brake that refuses to release. Stress piles up through the couplings. A junction, such as Cajon Pass, is the switch. Whether a rupture remains on one track, stops, or transfers onto another depends on the geometry and loading of the cars at the moment motion begins. Coulomb stress calculations try to measure the part of that loading most relevant to sliding. Shear stress acts parallel to the fault, encouraging movement. Normal stress acts across the fault, clamping the two sides together or relieving that clamp. Add friction, and scientists can estimate a Coulomb failure stress. A positive change generally means conditions have moved closer to failure. A negative change generally means the fault has been discouraged from slipping. But again, there is no universal threshold that works for every rock surface. The new studies model also includes viscoelastic relaxation. During a large earthquake, the brittle upper crust breaks quickly. Beneath it, hotter rock does not snap in the same way. Over years and decades, it flows slowly, redistributing stress back into the crust. That delayed response is one reason an earthquake can change the mechanical state of neighboring faults long after the shaking stops. This matters at Cajon Pass because the junction sits amid a complicated bend and branch system. A rupture approaching a bend must overcome changes in fault orientation and clamping. The topography of the mountains can alter stresses at the rupture front. Secondary faults can absorb or redirect motion. A rupture traveling at several kilometers per second is not making a conscious choice, but its propagation is controlled by whether the next patch of rock is close enough to failure and geometrically favorable enough to continue. Every large earthquake changes that memory. Imagine two neighboring bank accounts. Plate motion makes regular deposits into both. An earthquake empties one account, but may transfer part of its balance to the other. The deeper crust continues adding interest in the background. After centuries, the accounts may become highly unequal, or they may rise together. The new model argues that a through-going rupture becomes more plausible when both accounts are heavily funded at the same time. But here is the problem. The model's present-day accounts are heavily funded. That does not mean a small earthquake tomorrow will automatically unlock the whole system. Most small earthquakes remain small. Swarms occur without leading to a major rupture. A magnitude 4 near the Salton Sea can raise short-term concern and trigger careful monitoring, but it is not proof that the San Andreas is about to break. The same is true for animal behavior, unusual clouds, groundwater rumors, or a random sequence of moderate earthquakes. These signs have not produced a reliable prediction method. What scientists can do is monitor deformation with extraordinary precision. Networks of global navigation satellite system stations measure how points on the ground move over time. Interferometric radar from satellites maps broad deformation across the landscape. Seismometers record earthquakes too small for people to feel. Borehole instruments measure strain deeper below the noisy surface. Geologists trench across faults and read disturbed layers as a history book written in mud, peat, charcoal, and gravel. These measurements show a landscape that is moving every day, even when people feel nothing. The quiet is not inactivity. It is part of the earthquake cycle. Now, consider the human stakes. The 1857 earthquake ruptured through a much less populated California. Its fault break was enormous, but the official historical record lists only one fatality. That low number did not mean the earthquake was gentle. It meant relatively few people, buildings, pipelines, freeways, rail lines, and electrical systems stood in its path. Southern California today is completely different. Greater Los Angeles, San Bernardino, Riverside, and the Coachella Valley contain millions of residents and one of the most interconnected urban economies on Earth. Cajon Pass is not an isolated mountain gap. Interstate 15 carries commuters and interstate freight. Major rail routes move goods between coastal ports and the interior. Energy and communication lines cross the region. Water systems link distant sources to dense cities. Damage at one narrow corridor can create consequences far beyond the fault trace. The most useful warning comes from a scenario, not a prophecy. In the Shakeout study, more than 300 scientists and engineers examined a hypothetical magnitude 7.8 earthquake on the southern San Andreas. Their scenario estimated about 1,800 deaths, 53,000 injuries requiring emergency room care, approximately 1,600 fires, and about $191 billion in total economic losses measured in the study's period. Fire alone accounted for an estimated $87 billion. Water outages created major business interruption losses. Those numbers are not a forecast of what the new Cajon Pass model will produce. The shakeout rupture path is one hypothetical event, and the next damaging earthquake could occur on another fault or follow a different direction. Building codes, population, infrastructure, and prices have also changed since the scenario was developed. The value of the numbers is scale. They show how shaking becomes a disaster through broken lifelines, fire following earthquake, delayed medical response, displaced residents, and businesses unable to operate. The earthquake itself may last 2 minutes. The emergency can last years. Imagine the first 30 seconds near the rupture. Strong motion throws unsecured furniture across rooms. Masonry walls crack. Older buildings without adequate retrofits lose critical supports. Vehicles slow or stop as drivers struggle to understand what is happening. In mountain corridors, rocks fall onto roads and rails. At fault crossings, buried pipes and cables are pulled sideways. Automatic systems begin shutting down trains, elevators, industrial equipment, and gas flow where controls exist. Then the shaking spreads through sediment-filled basins. Soft deposits can amplify and prolong motion, meaning some areas far from the fault may shake harder than simple distance suggests. Tall buildings respond differently from short, stiff structures. Bridges sway. Water sloshes in reservoirs and tanks. Electrical equipment trips. Cell networks become overloaded by millions of calls. After the ground stops, fire becomes one of the most dangerous secondary threats. Broken gas lines provide fuel. Damaged electrical systems provide ignition. Roads blocked by debris slow fire engines. Water mains may be broken at multiple points. Fire crews can face dozens or hundreds of incidents at once, with pressure reduced in the hydrant system. Hospitals may remain standing but still lose functionality. Sealing systems, pipes, computers, generators, laboratory equipment, and access roads matter as much as the main structural frame. Staff may be unable to reach work. Patients may arrive faster than they can be treated. A hospital that survives physically can still become operationally overwhelmed. The difference between survival and catastrophe is often preparation made years before the event. Modern seismic design does not promise that every building will be undamaged. Its first goal is to prevent collapse and protect life. Retrofitting unreinforced masonry, soft-story apartments, vulnerable concrete buildings, bridges, water lines, and electrical substations reduces the number of failures that can cascade together. At the household level, the actions are smaller but immediate. Secure tall furniture. Keep shoes and a flashlight near the bed. Store water. Know how to shut off utilities when there is actual damage. Keep medications and copies of essential information accessible. During shaking, drop to the ground, cover your head and neck under sturdy furniture when possible, and hold on. Do not run outside through falling glass and masonry. Earthquake early warning is also frequently misunderstood. Shake alert does not predict an earthquake before it starts. Sensors detect the first waves after rupture begins, estimate the event, and send alerts ahead of the strongest shaking where distance allows. Depending on location, the warning may be a few seconds or tens of seconds. Near the epicenter, warning may arrive too late. Farther away, those seconds can allow trains to slow, surgeons to pause, machinery to stop, and people to take cover. Preparedness is not panic. It is the opposite. The new Cajon Pass research matters because emergency plans are built around scenarios. A rupture confined to the San Andreas creates one geographic pattern of shaking and lifeline failure. A rupture that crosses onto the San Jacinto Fault creates a broader and potentially more complicated pattern affecting additional communities and corridors. A joint rupture can lengthen the source, extend the duration of shaking, and challenge response systems across a wider area at the same time. Rupture direction matters too. Earthquake energy can be concentrated forward along the direction a rupture travels, a phenomenon called directivity. A rupture propagating toward a populated basin can create stronger, more pulse-like motion in some locations than a rupture moving away. The exact starting point, depth, speed, bends, and branches all shape the outcome. This is why scientists resist a single cinematic picture of the big one. There is no one script. There are families of possible earthquakes. The southern San Andreas can produce a major rupture without involving every nearby fault. The San Jacinto can produce damaging earthquakes on its own. The system could break in separate events years apart. A rupture could stop at Cajon Pass. It could cross. It could begin north of the pass or south of it. The next severe Southern California earthquake might occur on a different fault entirely, as the 1994 Northridge earthquake did on a previously hidden thrust fault. What, then, are scientists watching now? First, they watch the long-term deformation field. If satellite and ground station measurements show changes beyond expected plate motion, researchers examine whether the signal is tectonic, hydrologic, atmospheric, or an instrument problem. Seasonal groundwater pumping can move the ground. Rain and snow loading can shift measurements. Separating those effects from fault strain requires years of data and careful modeling. Second, they watch microseismicity. Tiny earthquakes reveal active structures and changing stress, but a cluster is not automatically a warning. Most clusters fade without a larger event. Scientists compare locations, depths, focal mechanisms, and migration patterns. They look for whether activity is occurring on the main fault, a branch, or a nearby geothermal zone. Third, they watch creep. Some fault sections move gradually at the surface. Changes in creep rate can be interesting, but no single acceleration or slowdown has become a reliable short-term predictor. Surface creep may also fail to represent what deeper locked sections are doing. Fourth, they refine the paleoseismic record. Every new trench can change the reconstructed timing or extent of an old rupture. If an event once believed to stop at a site is found farther away, estimates of past rupture length change. If two events once thought to be simultaneous are separated by decades, the model's sequence changes. The 2026 study depends on that history, so better history produces better stress estimates. Fifth, they test the model against alternatives. What happens if stress is not fully reset during an earthquake? What if slip rates vary more strongly along strike? What if a previously unmapped branch carries part of the motion? What if fluid pressure reduces friction on one segment? A robust result should remain important across a reasonable range of assumptions, or researchers should identify exactly which assumption controls it. Keep an eye on communication, too. A credible update will distinguish observation from interpretation. It will say whether a number was measured, calculated, or simulated. It will describe uncertainty. It will avoid announcing an exact earthquake date. A source that claims scientists are hiding a known countdown is not reflecting how earthquake monitoring works. The most realistic near-term danger is not that California will split in half or fall into the ocean. The San Andreas is a strike-slip fault. The plates move mainly horizontally past each other. California will not drop into a giant opening. The fault is also not capable of a magnitude 10 event. Its dimensions limit the maximum plausible magnitude, and the United States Geological Survey considers events larger than roughly magnitude 8.3 extremely unlikely on the San Andreas. The real danger is more ordinary and therefore more actionable. A major strike-slip earthquake producing violent shaking, surface displacement, fire, landslides, liquefaction in susceptible ground, and prolonged lifeline disruption across a densely populated region. The phrase highest stress in 1,000 years sounds like a timer. It is not. Earthquakes are irregular. A fault can remain highly stressed for years or decades. It can also rupture before a simple model reaches a historical maximum. Stress is necessary for an earthquake, but it is not the only condition. Frictional stability, fluids, damage, and the precise state of small fault patches influence nucleation. That uncertainty is frustrating because people want a date. Science cannot provide one. But uncertainty does not erase risk. A smoke alarm cannot tell you the date of a future fire, yet you still test it. A seatbelt cannot predict a collision, yet you still wear it. Earthquake preparedness works the same way. The new model gives planners a reason to examine whether existing scenarios adequately include joint rupture across Cajon Pass. It gives engineers a reason to consider geographically broader lifeline failures. It gives scientists a target for field observations and more detailed dynamic rupture simulations. And it gives the public a clearer explanation of why one mountain junction can influence the scale of a regional disaster. By the time we reached the end, the open question was what the instruments and models had actually captured. The answer is not a secret earthquake already underway. The San Andreas did not issue a supernatural warning. The unexpected result is that 1,000-year reconstruction places adjoining parts of the San Andreas and San Jacinto systems at exceptionally high modeled stress, while the difference between their stress states is moving toward conditions associated with past through-going ruptures. Cajon Pass may be a gate, and the gate state can change. There is currently no scientific evidence that a major San Andreas earthquake is certain in the coming days, weeks, or months. There is no credible exact prediction. The model itself has assumptions and uncertainties. But the smaller, closer danger is real. Southern California contains locked faults, accumulated strain, vulnerable infrastructure, and millions of people who may receive little or no useful warning before strong shaking arrives. So the responsible response is neither denial nor panic. It is preparation. Check whether your home has unsecured furniture. Know the safest place in each room. Keep water, medication, sturdy shoes, light, and communication options available. Learn whether your workplace, school, and community have a plan. Enable official earthquake alerts where available. During shaking, drop, cover, and hold on. And remember the personal question from the beginning. Have you ever felt an earthquake? Tell us where you were and what the first few seconds felt like, because those real experiences help other people understand that preparedness is not abstract. If this investigation gave you the full picture without the hype, help us reach the 5,000 like goal, subscribe for the next evidence-based disaster documentary, and share this with someone living in earthquake country. No filler, no guessing, just the facts and the full picture. Let us go. See you in the next one.